Hello, we're back. So I finished this table here, and 8 squared is 64, not 81. And 64 is 63 plus 1. So 64 is congruent to 1 modulo 9. And since we got a 1 here, we just repeat from then on. All right. So the interesting thing here is that in this column, it's all ones. Okay, and the reason that that's true is because we have um, a bar to the 1, a bar to the 2, all the way up to a bar to the k, where these form a subgroup of z mod and z times. And so by Lagrange's theorem, the order of this subgroup divides the order of z mod and z times, okay, which is the number of elements in there. So in this case, z mod 9z, the multiplicative group of that has 6 elements, and so the sixth power of each element is going to be 1. And the smallest power of every element that is 1 is going to be a divisor of the number of elements of the group. Right? So if you remember back the way we proved Lagrange's theorem, we had cosets, and we can partition the elements of z mod 9z according to the cosets therein with respect to some subgroup. So if I take the subgroup which contains the powers of 8, which would be 1 bar and 8 bar, then 2 is not among these. So let's take 2 times 1 bar. So 2 times 1 is 2, and 2 times 8 is 16, which is congruent to 7. So we get 2 bar and 7 bar here. And we've got, let's see, 4 and 5 are not in here. And if we put, so if we take 4 bar times 1 bar, we get 4 bar, and 4 bar times 8 bar is 40 bar, which is, sorry, 4 bar times 8 bar is 32 bar, which is 5 bar. So you see, we have our subgroup, which consists of powers of 8, and we have 2 cosets, and each of these cosets is of the same size. That's why the number of elements in the group is a divisor of the total of the subgroup is a divisor of the total number of elements. Now if I take the powers of 4, which would be 4 bar, 7 bar, and 1 bar, because this is 4 bar, this is 4 bar squared, this is 4 bar cubed. Then we see here that, for example, 2 bar is not in here, so 2 bar times 4 bar is 8 bar, so, and 2 bar times 7 bar is 14 bar, which is 5 bar. And this is again a partition of z mod 9z into a subgroup and a coset of the same size. So this is a partition into cosets. Right? So a special case of this is Fermat's little theorem. Because if P is prime, and A is congruent to is not congruent to 0 mod P, then A to the P minus 1 is congruent to 1 mod P. Okay. So this is always true. So what does that mean? So since P is prime, we have A being not congruent to 0 is the same thing as saying that A bar is an element of Z mod PZ multiplication. And so now the order of this group is going to be P minus 1, because all of the integers are, because Z mod PZ times is equal to these ones. Each of these numbers from 1 through P minus 1 is invertible modulo P, and or has a multiplicative inverse modulo P. So so there are P minus 1 of them. And so the smallest power of A bar that is congruent to 1 is going to be a divisor of P minus 1. So so that means that if A bar to the K equals 1, where K is the order of A bar, we have K divides B, divides P, so P minus 1, so P minus 1 is equal to K times L, let's say. So A bar to the P minus 1 equals A bar to the KL, which is 1 bar to the L, which is 1 bar. So we get that A to the P minus 1 is congruent to 1 mod P. All right, so that's Fermat's little theorem. Okay, so one new definition is that if the order of element A is equal to the number of elements in Z mod NZ, then A bar is called a primitive root modulo n. Okay, so if we look back at the powers of, if we look back at Z mod 9Z, we see that here 5 is a primitive root and 2 is a primitive root. So there are 2 primitive roots modulo 9. But you see for 7 and 8 and 4 and 1, we got 1 a long time before we got all the way out to the 6th powers, so those are not primitive roots. So one thing that we'll see later on is true is that if this number here, n, is prime, there will always be a primitive root. So that's is yet to come. Okay, so okay. Let's look at Wilson's theorem. Okay, so this is that if P is prime, then P minus 1 factorial is congruent to 1 minus 1 mod P. All right. So let's look at the elements of the multiplicative group. So let's look at 1 bar, 2 bar, 3 bar, P minus 1 bar. Okay, so each has, they all have multiplicative inverses. Okay, and so if one of them, call it x, is its own inverse, then let's say then x squared. Okay, let's use the number instead of the congruence class. So we have x squared is congruent to 1 modulo p. Okay, so all right, so thus another way to write that is x squared minus 1 is a multiple of p for an integer k. Okay, so x minus 1 times x plus 1 is kp for an integer k. So we get that p divides this product, which means that by the prime divisor property, which we have proved in 2 different ways, p divides x minus 1 or p divides x plus 1. And if p divides x minus 1, then x is congruent to 1 mod p. And if p divides x plus 1, then x is congruent to minus 1 mod p. So, which is the same thing as saying x is congruent to p minus 1 mod p. So the first and the last of these numbers, or congruence classes, is its own inverse, and every other one matches up with a different congruence class. And so we can pair the congruence classes with their inverses. Then the product, 1 bar times 2 bar times 3 bar times p minus 2 bar times p minus 1 bar, well, that's going to be equal to 1 bar, and then we're going to multiply all these things with their inverses and get, well, if I multiply something with its inverse, I get 1 bar, and then I'm going to get p minus 1 bar, so this is equal to p minus 1 bar. And so we get that p minus 1 factorial